Okay, well, I've got just a little after 1 o'clock, so let's get started. Good afternoon, good morning, everyone. My name is Jerry Hahn from Purdue University CERIAS, and I'd like to welcome you to the July 15th session of the CERIAS Summer Security Seminar Series. We're very pleased with the lineup we have in place, and I hope you'll benefit from hearing from cybersecurity experts and practitioners we've assembled at these weekly seminars. These sessions would not be possible without the support of the members of our CERIAS Strategic Partnership Program. To learn more about CERIAS and the CERIAS Strategic Partnership Program and how your organization may benefit, please contact info@cerias.purdue.edu. During the presentation, please keep your lines muted. We're going to have a very large crowd today. If you have a question, please submit your questions through the Q&A function. We'll also be monitoring the raise your hand function on the WebEx. It's my great pleasure to introduce our speaker for today. It would be an understatement to say that Joseph Weiss is considered an industry expert on control systems and electronic security of control systems. With over 40 years of experience in the energy industry, Mr. Weiss spent more than 14 years at the Electric Power Research Institute, the first 5 years managing the Nuclear Instrumentation and Diagnostics Program. Joe serves as a member of numerous organizations and task forces related to control system security. He is also a director on ISA Standards and Practices Board. He has provided oral and written testimony to 3 House subcommittees, 1 Senate subcommittee, and formal statements of record for House committees. He has also responded to numerous government accountability offices information requests on cybersecurity and smart grid issues. He is also an invited speaker at many industry and vendor user group security conferences, has chaired numerous panel sessions on control system security, and is often quoted throughout the industry. He has published over 80 papers on instrumentation, controls, and diagnostics. He has amassed numerous awards, certifications, and patents in the industry, and has been a featured speaker at dozens of conferences worldwide. He is a registered professional engineer in the state of California, a certified information security manager, and certified in risk and information systems control, and manages a very active blog on control systems and system security. With that, Joe, I'll turn the floor over to you.
Okay. Jerry, thank you. Can people hear me? I'm assuming, as I can't look out and see anybody. So the first thing is I wanted to thank Purdue for inviting me. The last time I was involved with Purdue, in a sense, was almost 20 years ago when they had a cybersecurity conference in Indianapolis. And I was the only person there really speaking about control systems. And I look back after about 20 years and ask, okay, so what's changed? Without trying to go through my background, what I wanted to do is get directly into the presentation. And I'm going to start literally with the title of my book, because that basically talks about why we're here to begin with. It's called Protecting Industrial Control Systems from Electronic Threats. And the reason for the title is hacking control systems is not that difficult. Protecting them is rocket science, because you have to balance between performance and security. If you put in too much security, you've essentially hacked the system. And we have an awful lot of systems that not only have no security, have no capability of being secure. Old term, when we first started the ISA 99, the International Society of Automation's cybersecurity standards, it was mostly oil, gas, chemicals, power. I was there for power, whatever. And it was industrial. So the term industrial control systems took place. If I had to do it again, I would not use the word industrial, because this is not unique to industry, industrial. And it's from electronic threats. I didn't say hacking because I didn't want to get focused on the proverbial 12-year-old pimply-faced hacker writing malware for Windows. This is a lot more than that. In fact, the reason I had changed it is I was at EPRI till 2002. I had started the control system cyber program in 2000. And when I left, I had a lot of pressure to start a control system cybersecurity conference because none existed at the time. When we had our second conference, this was in April of 2003, we still didn't have a SCADA testbed. Idaho didn't exist yet, the SCADA testbed. So I had invited a number of entities that had testbeds to speak about why they should be. And one of them that spoke was the U.S. Navy Mission Assurance in Dahlgren, Virginia. And their first slide, again, this was supposed to be, why are you a test range? Their first slide was a Navy ship was coming into the port of San Diego. And instead of having its high-powered radar turned off, it inadvertently had left it on. And it took out San Diego Gas and Electric and the San Diego Water Authority system. It was every bit as much, in a sense, this was son of EMP, son of electromagnetic pulse, EMP. But it was basically high-frequency electromagnetic interference, radio frequency interference. The second slide was that while doing radar testing in Europe, they blew up a 36-inch pipe. Very much, a kinetic issue. And, I've been around for a long time. My big thing is I come from the engineering world. And so when I deal with cybersecurity, I'm not looking for vulnerabilities. I'm looking for impacts. What can you do? So first of all, control systems, what are they? They're anything that monitors, measures, or controls a physical process, whether it's...
Joe, this is Jerry. Are you sharing your screen?
I thought I was.
Okay, no, we're seeing the cover slide still.
Oh, okay, hold on. Let's see, what do I need to do for the screen sharing?
In the menu, there's a share.
That's what I'm doing.
Under there, there's both share screen and share
There
you
okay,
go.
you see it?
Yep, just go into presenter mode and you're good.
Okay, sorry about that. So anyways, let me bounce. Okay, can you see slide 3?
Perfect.
Got it. So the point being, control systems are not just everywhere. Water, power, warehousing. What you see in the bottom left is a ventilator. Think about, COVID. Those ventilators are really heavy-duty control systems and everything that goes with it. You have mass transit, shipping. The body is a control system, or the brain, if you will, is the master station that's controlling blood pressure, heart rate, everything else. This is very, very, very much a universal type of situation. And they're also the things that people really, they've been called the invisible visible. They're everywhere and nobody sees them. So this is distributed control systems. This is SCADA, supervisory control and data acquisition, programmable logic controllers, remote terminal units, intelligent electronic devices, sensors, actuators, drives, power supplies, chemical analyzers, you name it. Now, this is important because this is, let's make sure we're even on the same page. Ironically, I'm talking to Purdue. This is the Purdue reference model. This is not the OSI stack. This is the Purdue reference model. And what you're looking at is actuators, drives. This is where you control a process in real time, in milliseconds. Then you go up to, if you will, this was broken up by time. So you go up to seconds to minutes. Then you go up to minutes to hours. Then you go hours to days, days to weeks, months. And finally, you're all the way up at the internet. What's happening is we are living at that lowest level. Now, the next really, really important thing is what's a cyber incident? Because this is where there's a tremendous amount of confusion and people need to understand what it is and why. The de facto IT definition is your stealing your data. It's really about privacy. Currently, NIST has a bunch of definitions. The one I've been using, and I used that when I was supporting NIST, when we were trying to extend NIST 853 for control systems, is electronic communication between systems that affects confidentiality, integrity, or availability. There is no mention of the word malicious. NIST very consciously did not use the word malicious. And that's terribly important because in a lot of cases, we'll never know whether it was malicious or not. Not only that, a sophisticated hacker will make a cyber attack look like a malfunction. Or you have something that's caused, and the only difference between malicious or unintentional is intent. How do you measure intent? So what everybody needs to understand is, as I'm going through this, and I'm talking about cyber incidents, it doesn't matter, in a sense, if it's malicious or unintentional. I'm worried about what can be the effect. Next, under confusing terms and definitions, lots of people use the word smart for different things. Smart cities, smart grid, smart manufacturing, smart sensors, smart water. You've got the Internet of Things, you got digital transformation. I've heard Internet of Battlefield, name it. The only thing about what smart means is you've got two-way communication and it's programmable, which means anything you use the word smart with is cyber. What I mention here now is are lousy marketers. Digital system in almost every industry since the mid-90s. Not mid-2000s, mid-90s. We just never, and we were using smart. We were connecting these digital systems. We were having both internal and external networks. We just never came up with buzzwords like digital transformation, Industry 4.0, IIoT, or smart, whatever. But we've been doing that forever, or it seems like forever. The other point is everything starts with analog, because that's Mother Nature. And then it's converted to digital. But even when you talk about digital, everything still starts with analog. Another really important point is what is operational technology, OT? People throw that term around left and right, and they also are constantly talking about the IT-OT convergence. Well, unfortunately, to very many people, OT is the network. It is not your pumps, valves, heat exchangers, relays, capacitor banks, conveyor systems. It's the networks. Most, I'm using this term and I probably shouldn't, but most engineers or technicians do not consider themselves to be part of OT. If you talk to most of them, they've never even heard the term OT. OT is coming out of the security world very differently, okay? Another term that really puts us at odds is a lot of people use the term cyber physical. Cyber physical makes it as if these are cyber systems that have some physical component. It's the opposite. We're physical cyber. We're physical systems. We're pumps, valves, heat exchangers, motors, relays. That's physical. They just happen to have cyber connectivity. And this is why there's such a big problem when you don't have the engineers as part of this issue. It's their equipment. There's a big issue about endpoints and edge devices. The IT, endpoints and edge devices, are often routers, switches, cell phones, tablets, maybe some type of gateway. To us, an edge device is a sensor or an analyzer. It's a physical device, part of your process system. Now, the last one I want to talk about is really important for a lot of reasons. I think most people would view Stuxnet as a cyber attack. What Stuxnet did is it changed the control logic, then had the control logic change the process, and then changed the control logic back so nobody knew what happened. Well, what I just described is the Volkswagen cheat. And by the way, not just Volkswagen, Fiat Chrysler did the same. Basically, they had come up with diesels that, when they developed them, met EPA requirements, and billions were spent to make them as efficient as possible. Changed and they couldn't be met. So what certainly Volkswagen and Fiat Chrysler did, I bring that up because they were caught and fined. What they did is they actually came up with logic to change the fuel control and the emissions control while the car was under test, so that they could pass the test, and then they changed it back afterwards so you get your 45 miles per gallon. It was exactly what Stuxnet did, but without trying to break things. Well, a couple of points about this. Number one, it brings up that insider doesn't have to be a rogue employee. These were rogue companies. Number two, malicious doesn't have to be. In this case, it was damaging the atmosphere, the environment, and it was reducing the value of the car. The third thing about this also was there is this feel by way too many people within the quote-unquote OT or non-engineering community that all control systems have an HMI, a human-machine interface, this Windows display. Well, one of the things about the Volkswagen cheat scandal is there's no HMI. The only HMI would have been for the people doing the testing with scope. Emissions or your fuel control, environmental emissions. So the point that somehow you have to have an HMI is wrong. The other last point on this before I go to the next slide is this was huge. The Volkswagen cheat scandal affected something like 800,000 cars and trucks. The Fiat Chrysler affected over 100,000. In my database, I counted each of those as one, just to give you an idea of what is really out there. Now, how did we get here? Prior to 9/11, cyber was just another risk for reliability and safety. And it turns out engineering owned everything about their equipment, including cyber. And the concept of having somebody from IT running out and playing with a control system network would have been heresy. Well, following 9/11, cyber became national security, and it was moved to IT. Now, I don't have a date, and I don't have a piece of paper, but that is everywhere. And when that occurred, IT, cyber, and by the way, you can substitute the word OT, it doesn't matter, same difference. To IT or OT, cyber was the Internet or Ethernet network. It was not at all the part of the, so all of the control system equipment fell off the table because sensors, actuators, drives, power supplies, chemical analyzers weren't considered to be part of So to this day, we have no cybersecurity or cybersecurity requirements for any of these legacy devices. The other thing is that we use the noise, the fluctuations in a signal to tell you about the health of a process, the health of the sensor, the health of the process itself. Well, it turns out that the HMIs were never designed to capture this higher frequency data. So here we are, less knowledgeable of what is happening with the actual process with our IP networks than we were from before. Now, this is the epiphany and why I changed the title of the presentation. Because it dawned on me, cybersecurity is like building the Maginot Wall during World War II. Cybersecurity grew out of IT, which was growing out of protecting networks. And if all you're doing is protecting the network, spending all of your protection around the networks makes sense. When it came to control systems, that same thing occurred. The thought was, we have to protect the network. Not we have to protect the network and the equipment, we just have to protect the network. That's the Maginot Line. For those that aren't aware, May 1st, President Trump issued an executive order on cybersecurity, the bulk electric system. And that was because the Chinese managed to get basically hardware backdoors into large equipment behind all of these network monitoring systems. In other words, just like Germany went around the Maginot Wall, in this case, the Chinese went around the Maginot Wall of all of our cybersecurity protection. Now, this is an important slide for the non-control system people to understand where we are and what we are. The control system, starting from on my right, I don't know if it'll be your right or your left, is IT-ish in nature. Here you've got your internet. All of this to here is normal IP, though it may have some controls, protocols and wrappers, but this is very much what anybody in traditional networking would understand. Here is your HMI, your operator displays. And prior to Stuxnet, this is as far as security went. Because of Stuxnet, all of a sudden, programmable logic controllers were now being included in security. So ironically, a friend of mine is just now starting to put together, if you will, a top 20 list of secure PLC programming. Like within the past couple weeks. How can that be that we've had no guidance for secure coding for programmable logic controllers to this day? Now, you move to the left further, you get to control valves, motors, sensors, analyzers. There is no cybersecurity there. There is no authentication. And there's no cyber logging at this level. The lower level networks for this, like HART, Profibus, Serial Modbus, have no security. Over here, which is where you go boom in the night, is where we have no security. Kind of ironic. Now, control system cyber incidents are real. I go back to the fact of we're talking, it does not have to be malicious, and in many cases we wouldn't know. I've been able to identify more. Chrysler is 100,000. There's been over 1,500 and well over $70 billion in direct impact. What you're looking at here is complete destruction of a turbine. This is the Aurora hardware test. This is DC Metro train crash, the San Bruno natural gas pipeline rupture, the Bellingham, Washington gasoline pipeline rupture, the Rucci wastewater hack. This was hacking the buoyancy and tilting an offshore oil rig. This is the complete destruction of a 6,400 megawatt hydro station in Russia. I always have trouble with the name. That killed 75. The hydro plant is about 1.5 times as big as the biggest one we have in the U.S. This is a brand new Navy ship that never even made it to its home port because of control system cyber issues that took out the propulsion. I had 2 other interesting ones, literally over the past week. And part of this also says, guess what? Our information sharing doesn't work. One of them was dealing with a a drinking water system, where somebody had hacked into, changed the pumps, changed configurations, and everything else was caught. And he's now up for sentencing. I had gotten a call trying to find out, gee, could he have hurt anybody? Because they're getting ready to sentence him. The other was, again, we'll be talking about the executive order. This was the compromise of a clean room in a pharma facility. What you're seeing is this has nothing to do with any industry. This has to do with every industry. And it has to do with resilience and recovery. And what does that mean if we can't trust what we have? This is a really important one, and it also goes to every university. What you have on the left, the big circle, is the networking world. I changed. It used to be that this was IT and on the right was control systems, but it's changed. What you have is computer science. My first reaction is, can you please tell how a pump exchanger and RTU, what they work and what the sections are associated with those? And if you can't, how can you tell me you really understand the process? And the whole issue is, what you have is not the IT-OT convergence. You have the divergence between packets versus process. And what we care about is the process. Now, as far as cyber threats, new slide, our most probable cyber threats are the unintentional or the network security people, whether it's IT or OT, doing things that actually impact our control systems. And yes, this has happened many, many, many times, and will continue to happen more until the engineers are brought in. For malicious attacks, the real concern is that there's only X number of and that's the same way in the world. If you know how to run a water water system in one country, you pretty much know how to run a water system in another country. We only have X number of vendors who make the things, which means it's not one industry that can be impacted, it's every. And oh, by the way, Russia, Iran, China, etc., are aware of this. I brought up before, why are we talking about unintentional? Because a sophisticated attack like Stuxnet, etc., will be made to make a cyber attack look like an equipment malfunction. We have limited control system cyber forensics when you're below the IP level, and we have almost no training for the control system or safety engineers on cyber. Almost all of the training today is for the network people. And we have major culture and governance issues, which I'll go through next. You know, one of the things that keeps being brought up are cybersecurity frameworks. And that includes in DOE's recent request for information on the executive order. All of the frameworks for cyber are IT focused. They are not process focused. Even the Solaris did not address the unique issues associated with control systems. Networking and engineering, whether you call it IT or OT, have different priorities and different knowledge bases. We need them both, but you can't have one doing something to the exclusion of the other's necessary constraints. And cyber decisions are way too often made with no engineering participation at all. This is my view, my latest view of the IT-OT differences. One of the biggest is this concept of zero trust. IT-OT, you're not supposed to trust anything. Engineering, you trust everything. That's why when I get to the point where the Chinese had made counterfeit process sensors, why it's so devastating. That's 100% trust. One of the biggest things that people need to get out of this presentation is for IT or OT, all comms go through the IP network. So if you're monitoring the IP network, that's okay. But for the engineering, for the 0-1 devices, you can get to them without going through the IP network, which means if you don't look at the actual control systems and devices, independent of the network, you're blind. You're also not safe. This last point I wanted to get across. Attackers are becoming better system engineers than the defenders. That's a horrible thing to say. This is just a couple of examples of IT control system issues. What you're looking at here, this is right out of the NASA Inspector General's report. And what you're looking at is a security patch update that was intended for standard IT systems, resulted in the oven temperature rising and a fire that destroyed spacecraft hardware in the oven. And it was undetected. You know, these are real problems. Another one was vulnerability scanning. Now, in this case, it was active. Vulnerability scanning caused a loss of communication with a satellite, making an orbital pass useless. These are really big deals. The misconceptions that, you know, a SCADA HMI, a master station, the HMI is used in all control systems. Like I mentioned with the Volkswagen case. That's not true. SCADA HMI is needed to keep lights on. Again, not true. We've already had one utility who had its SCADA system targeted and hit. And they lost SCADA for 2 weeks but they did not lose power. Operator can prevent damage. Absolutely not in many cases. Because if it's at the low-level devices, that's occurring in milliseconds. When I was in nuclear doing nuclear safety, the Nuclear Regulatory Commission gives no credit for any operator action for 10 minutes. And that's even assuming the operator is given the right information. Like I say, control system devices can be accessed from outside the Ethernet network, just inside. Control system anomalies, many of them cannot be found from within the Ethernet network. It's necessary to monitor the Ethernet network, but it is not sufficient. My big thing, and I'll be going through this in more detail, sensors, field devices are assumed to be uncompromised, authenticated, and correct. In other words, everybody is assuming, and I use the word everybody to the 99.x%, assume that the sensor input into the network is correct and uncompromised and authenticated, and it is none of that. Maybe it's correct, maybe, but I did work long before I got into security to show that sensors drift. They may not be as secure as as correct as you think. Vulnerabilities do not equal system impacts. I don't care how severe the network vulnerability is, until you can tell me which pump, valve, or heat exchanger or relay it impacts and how, I have no idea what to do. And security does not equal safety. This is from Moody's put out, I just got copies of it a couple of days ago. And these were some of the things I pulled out of it. Companies will work to better protect OT networks. True. But what about the hardware? The whole point of the presidential executive order is the hardware. OT security offerings will evolve and organizations will be better prepared to detect and recover from cyber incidents. We can't even be sure we can detect a cyber incident. The Triton event in Saudi Arabia tripped off a petrochemical plant because of that malware, and nobody knew. They restarted with all the malware. This one really, I think it's really important for everybody to know. Physical assets operating in the OT environment only recently began to adopt digital technology in a significant way. This is absolutely, positively wrong. In 1996, when I was at EPRI, I established the Instrumentation Control Center at the TVA Kingston Steam Plant. And it was to demonstrate the benefits of upgrading from analog to digital. You know, we've had digital technology in our systems. You know, oil, gas, chemicals, water, not everybody, but a large percentage, manufacturing, for 15 to 20 years. We just haven't used the right buzzwords. And it also, this is about the supply chain. Weaknesses across software installations can cause substantial damage across industries. Absolutely correct, but weaknesses across hardware installations can be even more damaging, which is really the executive order. Cyber does not equal denial of service. It may in IT. It certainly doesn't here. If the worst case you could do would be denial of service, we wouldn't have a problem. Our issue is this can be existential. You can bring the grid down for 9 to 18 months by damaging equipment. The biggest threats don't need to be APTs, advanced persistent threats. Some of our most critical equipment can be damaged by some of the most simple and oldest cyber exploits. And the whole point that I brought about, we are physical cyber, not cyber physical. Aurora and other events like that is not malware. What you're doing is using cyber to push it into a forbidden operating zone where nature will destroy it. That's why you must have the safety does not equal security. Somebody brought this up, I thought it was great. Safety is what is expected. Security is what is unexpected. I'm working with several different standards organizations trying to figure out how to, if you will, coordinate safety and security. That is not done yet. And the level 0-1 devices are just assumed to be correct and secure. Literally less than a month ago, we put out in a joint ISA 84 safety, ISA 99 security working group, the first annex on cybersecurity of process sensors for safety. This is one that, again, is really, really important. All of our equipment have sensors as safety interlocks. The simple way of thinking about it is think about your home office shredder. If you put too much water in, too much paper, what's going to happen is that shredder will stop and it won't start until that temperature sensor goes back to normal. Until that time, that shredder is a brick. I could have prevented, or anybody like me, could have prevented DARPA's Plum Island test from even starting because they used a diesel generator as the black start, in other words, to get the grid going. If you would have changed the sensor readings on that generator, you could have prevented it from ever starting. This is why, and sensors cannot be bypassed. And we have no forensics there today, or minimal. This is where the real safety, reliability, and productivity occurs, is at the sensor level. I mentioned the physical cyber attacks. And this is also, in my mind, what was going on with the executive order and what's going on with the transformers at WAPA, at the Western Area Power Administration. Stuxnet and Triton were meant to destroy equipment without, and their intent was to make the attack look like equipment malfunction by confusing the operators and replaying displays, etc. What happened with Stuxnet was for a year, the centrifuges were being destroyed in Natanz in Iran without anybody having a clue it was cyber. They thought it was a systemic design failure. In June, like I say, June 7, 2017, that petrochemical plant in Saudi Arabia tripped. And it tripped because of that Triton malware. Only nobody really addressed or identified the fact that the malware was there. And they restarted. Isn't it something? Think of all of your requirements. If we can't even detect that, now, why the presidential executive order? For those that don't know, May 1st, President Trump issued an executive order 13920 on cybersecurity of the bulk electric system. And it occurred because they found extra electronics inside a large electric transformer. This should have never been there. There is no reason for that to have been there other than to have backdoor access directly into the system. What that backdoor access will give you is the ability to bypass cybersecurity and engineering safeguards, potentially cause unexpected operation or confuse operators. But it also gives the attackers, in this case, this coming from China, to monitor the power to know when we're most vulnerable. The real concern for me is, if you're going in through that back door, you can either change the sensor readings or the apparent sensor reading, and the equipment will act accordingly. You don't have to compromise the equipment. You just need to feed it the information you want to feed it, and it'll do exactly what the sensor readings tell it. Size of the problem, again, the reason for the executive order. There's over 200 Chinese-made transformers in the U.S. energy sector. And by the way, there's other Chinese-made equipment, software, and chips. And Chinese-made equipment is used in multiple industries, not just electric and not just in the U.S. The whole point is the potential scope and impact is unknown. This is what's in the executive order. And I think it is a great executive order, and it's late in coming. This addresses everything in black is what is explicitly in the executive order. What I have in red, items not included in the preceding list and that have broader application of using a power system are outside the scope of this order. Isn't that something? Your firewalls, routers, switches, that would be the network security, is outside the scope of the executive order. There have been counterfeit parts found. This can cause to this critical equipment that can take a year or two to repair or replace. It can affect, like I say, the device. It can cause injuries, can affect, in this case, load balancing. There's really no information sharing on this. And this is a knockoff. This particular vendor, who the Chinese did a knockoff of, is used in many, many non-Chinese made transformers. This is one that really got me started. This occurred in May of last year, where in this case, Yokogawa put out a notice to their customers. They were finding counterfeit pressure and differential pressure transmitters in the North American market coming from China. This is hardcore safety. Pressure level, flow. This is your safety input. And I found this is almost all of our vendors. And you can go today to Amazon or eBay and find these transmitters on there. They are either used or counterfeit, because none of our transmitter vendors use Amazon or eBay as an authorized distributor. What technically needs to be done? Well, the procurement requirements need to be reassessed. We have no cybersecurity requirements for field equipment and field devices yet. I'm working on, or we had a special working group within ISA 62443-4-2, that's the component spec. Because the only thing it says there is, if you can't meet the requirements, use compensating controls. But it doesn't spell out what that is. Supply chain needs to be validated. I mean, you saw that from Moody's. This is in the executive order. We need to know what's installed. We need to understand, are they counterfeits or not? Is the data good or not? Are there hardware backdoors? Is the data coming from where we thought it's coming from? This is sensor technology. This is not network technology. There needs to be improved information sharing. This is not just electric. Like I say, on Friday, I was informed of a pharma facility that was compromised. Basically, China had installed shadow sensor network in a pharma clean room with all of that data being exported directly to China. What's just as scary is, as best as we can tell, this was just exfiltrating data. Doesn't take much to change the, if you will, the environment in a clean room to cause great damage. We've got to address the governance issues between the security, the CISO organization, and engineering and ops. In this case, it turns out it was the engineers who found these devices that were in there, not the security people. This basically says, it goes back to the frameworks. The frameworks were never meant for control system issues. They were meant for network issues. We've got remote overseas connections because you've got international vendors. It's not to say not to have them, but we better make sure that they are, if you will, authorized and valid and necessary. And the idea of having field support from countries that are not necessarily considered friendly may also need to be reconsidered. Now, what can you do if you can't stop the attacks? You know, people keep talking about resilience without ever really talking about the technology. We got to get over the culture gaps between security and engineering. We have to isolate our non-securable devices to the extent possible. These are very much system interaction problems. I told you the bad guys are becoming better systems. We have to understand how do we make sure that this can't remotely cause a devastating problem. We need to develop appropriate control system policies and procedures. And based on things that have really happened, not hypothetical IT network issues. We've got to develop the appropriate system architecture. Now again, we've got within ISA the zones and conduits. We've had a whole bunch of discussions because with new technology, we go over these zones and conduits. Now, what's the best way to do this? We have to train the engineers to identify what possibly could be cyber-related events. I actually did that for the International Atomic Energy Agency by taking, a bunch of real nuclear plant control system cyber incidents. And a network diagnosis. And here's the other big thing. I don't believe, and this is me, that we're ever going to be able to fully secure a control system network. We have to be able to know whether we can trust what's happening. And we also need to be at a point where they can't hack what we're doing. And that means change the paradigm. Before the IP networks came around, we lived with monitoring the process sensors for not only performance, but for health detection. We have to be able to go back to the future because that's also the only place where we can go where you really can't hack it. It's the only thing that can basically get you away from much of the hacks that are going on today with ransomware. This is beneath where ransomware can get to. We need to be able to know what it is we need to protect and why. Because we need to know where the real risks are. The benefits from changing and going to this approach is we make an intractable network problem a tractable engineering problem. And this requires collaboration between engineering and networking. For universities, between computer science and engineering. When you do this, it's agnostic to why something is happening. It's telling you something is happening. Isn't it something that by doing this, it's not going to necessarily tell you it's supply, it's cyber, it's sensor drift, it's a loose screw, or the attachment holding the sensor is broken. We just need to know something has changed, go look. We're creating real return on investment by validating and optimizing the actual process operations. This is not insurance. This is hardcore reliability, safety, productivity. It's really real predictive maintenance. And it reduces the cyber threat space and improves safety. And given the fact that we're getting all of these new IoT devices, much of them have no security whatsoever, we've got to be able to have an idea what's happening. The Holy Grail, combining what's been going on with the network, what's been going on with the engineering world. Isn't it something they haven't done this yet? And I say this as a general statement. I mean, there's always probably somebody who's going to say, but I have. But the point being, this got to be able to make this interconnection. Finally, the recommendations. We've got to modify the governance to include all of the affected organizations. And the issue is, these are engineering systems. Who better knows the engineering system than the engineers? Before this whole thing, before 9/11, the engineers went to IT when they needed IT. We need to have that type of thing. These type of systems, and this isn't just for the end users, this is also for the vendors. Because the vendors make things too. We have to develop control system cybersecurity policies based on actual incidents. So we're actually trying to address what can happen, not what somebody thinks might happen. I go back to the Maginot line. The Chinese simply went around it. We have to assure other policies do not impact control systems. This is a really big deal. I mean, this was part of the reason ISA 99 started. All of our, if you will, alarm management can be divided into two pieces. One is you've got your SOC, your Security Operations Center or Network Operations Center, and it's monitoring all of these alarms and displays for security. Now, you've got the engineering there's got to be. The whole point, again, my nuclear background, and so I apologize for using those terms. We have to assure that cyber cannot exceed design basis, and that cyber can't create a problem we haven't already designed for. And by the way, it has in a number of times. This is your risk. We need to monitor the sensors in real time. We need to train the engineers. And we need to incorporate that into predictive controls and maintenance programs. And like I have on the last, this isn't just for industry. This is every bit as much for the universities. So anyways, this is I have no idea if I've run out of time. And if we've got questions, Joel, I'll leave that to you.
Hey, Joe, thank you very much. This is Jerry. And we we do have a few questions, and yes, we have run out of time, but just to be careful of everyone's time and respectful of their time, we can capture the questions we have and even any that come in while we're still here. And we can send those questions to you. And if you could respond to them for us, what we'll do is we'll post them on the website along with your presentation, if that makes sense. So with that, I think we will defer the Q&A instead of a live Q&A. We'll go ahead and capture the questions, ask Joe to provide his responses, and then we'll post them along with the video when we get this posted onto our website. So with that, I really do want to thank Joe for spending the time with us today. It was a very eye-opening and provocative talk. I think there's a lot that needs to be done, a lot that can be done, a lot that should be done. So we appreciate getting your views and the benefit of your years of experience with that. So as we mentioned, all these presentations will be available on the website, and you can see in the chat where those are on the Purdue, on the CERIAS.purdue.edu website. You'll be able to find our all the videos from the summer series. Plus, we'll post the Q&A from this session there as well. I want to thank everyone again for taking time to participate. Appreciate your time. Next week, we have an interesting talk coming to you from Sam Curry. He's pretty well known in the security industry. He's the Chief Technology Officer for Cyber Reason. And we're looking forward to seeing you again next week. So with that, Joe, thank you so much. We appreciate your time. And we'll be back here next week.
Thanks.